This is topic phenol from chapter 30 hydrocarbons. Now, what is phenol? Phenol is basically a compound in which a benzene ring C6H6 is attached to a hydroxy group. You can say it is quite similar to the family of alcohols, where we have an alkyl group attached to a hydroxy group. But here we have an aryl group derived from arene, this benzene molecule attached to hydroxy group. Phenol is acidic like alcohol, but it is more acidic than alcohol. Now, what is an acid? Any substance that tends to donate a proton. Now, why is phenol more acidic than alcohol? This is because when H plus leaves from the hydroxy group, we get something like this. Now notice this oxygen atom has gained a negative charge. It basically has a free p orbital with two electrons, and these electrons take part in the delocalization of electrons in this ring, making this product, the phenoxide ion, more stable. And when a product of a reaction is more stable, the reaction is more likely to occur, which means a phenol is likely to donate a proton. Meanwhile, alcohol here, when we see the product has an alkyl group attached to this oxygen atom, and an alkyl group has an electron donating effect. So this alkyl group tends to push the electron cloud towards oxygen atom, you know so they make one end of the molecule very negatively charged, and thus this product is not as stable as the phenoxide ion. So that is why phenol is more acidic than alcohol. Okay okay now, although phenol is more acidic than alcohol, it is still not as strong as an acid as sulfuric acid or nitric acid. So generally it is said that phenol is a weak acid. Okay. Now obviously it has acidic properties. It reacts with alkalis like NaOH to produce salt and water, something which alcohols can't. And it also reacts with molten sodium to produce salt and hydrogen. Phenol also reacts with bromine water, something which benzene does in much harsher conditions. The brown water decolorizes, and this is what the reaction looks like. Okay. Now, why does phenol react with bromine water, and why does substitution take place at specific places? That's because OH is an electron donating group. It donates electron to benzene ring, making it more reactive to bromine, and it specifically donates more electron cloud to carbon atoms near it, like carbon 2 and carbon 6, and carbon atom directly in front of it, like carbon 4. Okay, let's study some other reactions of phenol. For example, phenol with dilute nitric acid. Now, since phenol is basically benzene with an electron donating OH group, the reaction is very similar to the reaction of nitration of benzene. But now we have an electron donating group attached to benzene, which increases its reactivity as there is greater attraction between benzene ring and electrophile. So we don't need the concentrated sulfuric acid catalyst, and phenol is also fine with the nitric acid being diluted. Our products are 2-nitrophenol or 4-nitrophenol. Here I've shown the mechanism of phenol forming a 4-nitrophenol, but we can also form a 2-nitrophenol. Now I know some of you must be confused that why don't we form a 6-nitrophenol, since OH donates electron cloud to 2, 6, and 4. Why don't we form a 6-nitrophenol? That's because 6-nitrophenol is basically the same as 2-nitrophenol. Okay, it's just shown to you in different ways. Now, for example, a seller is trying to sell your muffler, okay, and that muffler has this one yellow block, okay, and the price is, for example, I don't know, $4, and then he offers you another muffler for $3, which is basically the same but shown you in a different way. So you'll be like confused, right? Because they're the same thing. So that is why 2-nitrophenol and 6-nitrophenol are also the same thing. Okay. Now again, if you use concentrated nitric acid, basically harsher conditions, you will get 2,4,6 trianitrophenol. Federal Karp's alkylation of phenols. Now you have studied alkylation of benzene, and the process is basically the same. Okay, I'm not going to repeat the whole process, but the only difference is that the OH group influences the position of electrophilic substitution. The OH group will only allow substitution to occur at carbon 4 or at carbon 2 or at carbon 6. The same thing happens in acylation. Okay, again, the same thing happens in acylation. Okay, I think I missed the arrow here. There's a bond between C and Cl here, and there is this curly arrow from Cl to AlCl3, and we generate our electrophile, and the electrophile then goes to electrophilic substitution, and we form HCl, AlCl3, and this thing right over here. Okay, esterification of phenols. Phenols also form esters. Now, if you remember from your AS chemistry, carboxylic acid and alcohols form esters when reacted together. And phenol also forms esters. Phenol forms phenyl esters, okay? But phenol does not react with a carboxylic acid to form ester. It never reacts with a carboxylic acid. Phenol reacts with acyl chloride to form an ester. Here you can see that this Cl and this H combine to form HCl, and we have our phenyl ester. Why it is an ester? Because we see the functional group for ester here, C double bond O, and then it is attached to O, and we have our phenyl ester. Okay, now phenol also reacts with acid anhydrides to form a phenyl ester. Here we can see that this H and this group highlighted in blue combine to form a carboxylic acid, and this yellow part and this yellow part combine to form a phenyl ester. That's all for today. Thank you.